As Sydney said, my name is Rich Graham, and I'm going to talk a bit about our technology, its current state, and where we're leading up to. If you have any questions, feel free to ask questions and to just interrupt and ask questions, and I can answer them. So first of all, in terms of current state of use of the technology, we're currently with our ADR at the EDR generation of our technology, the 100 gigabit per second technology. In terms of use in the top 5 in HPC, in the top 500, the network is used in 4 of the 5 systems. So the number 1 and the number 3 systems are the DOE Coral systems. Number 1 is a system at Oak Ridge, and the number 3 is a system in Lawrence Livermore Lab. These just made the list this last June at ISC. The system in China is also the number 2, using 41,000 endpoints, and uses our interconnect. Other places where that are visible that use our interconnect also is at AIST. They have the largest AI system in Japan, also number 5 in the top 500. And we have also a system, a notable system at number 13. Another interesting system that's in the process of being built right now is a large ARM-based cluster at Sandia National Lab named Astra. 2,500 nodes of ThunderX2, and they're using our InfiniBand as the interconnect there. So a bit about the direction or the philosophy we use in helping determine our path forward with respect to new technology that we generate. So we always worry about speeds and feeds. So we always worry about wanting to make sure we have at least the best, if not a generation ahead in terms of bandwidths. Latencies, we have very low latencies. Very high message rates. Switch radices, we have fairly large switch radices. So we want the basic features that are important to build a system. We always worry about those. Always make sure that those are leading edge and provide what's needed for solutions. But beyond that, beyond the speeds and feeds, what really helps us, what really gives us direction is what we call our data-centric approach, where we look at overall how the network fits within the overall system, and not just how does the network work in a ping pong benchmark or something like that. So we look. At using the network to optimize algorithms to help throughput on applications, and not just pass data. Of course, it passes data, passes it very, very well, but it also has other characteristics that we add to it, so that we can make a system more efficient. So most systems, other networks, most of the work is done at the endpoint. So anytime you want to touch the data that's remote, you have to bring the data from one side of the system to the other. You have a transport problem. You may have to transport, if you're in an algorithm, you may have to transport the same data multiple times. We try and we develop algorithms to reduce the number of times you need to actually transfer data, and be able to operate on the data as it's moving through the network. And I'll talk briefly about one of the instances in a while. So this is really a big differentiator. We try very hard to avoid the CPU, even from day one, with first cards, let the CPU be used for the application, for the computation, what it's designed for, and not to handle the network stack. That we offload as much as we can to the network. So a first set of targets that we worked on in terms of offloading is offloading communication algorithms, specifically collective algorithms. So instead of in a collective algorithm, optimized collective algorithms, depending on what algorithm you're talking about, a lot of times if you're doing the computation at the endpoints, you have to transfer the data multiple times between the endpoints. So one, you use a lot of data, a lot of network bandwidth that you don't really need to use if you design things differently. You cause congestion in the network. You make the CPU work on things that it really shouldn't. The CPU should really be working on the application. Instead, we move those operations into the network, and so it's basically a fire and forget. That's the philosophy here. So you get, and I'll talk more about specific instance here. So we're aiming. We always want to continue reducing the network latencies. So we always would love to have ping pong network latency at 0. Speed of light causes us a few problems there. So we really are to the point where there's not a lot more to extract out of the silicon. We're really getting close to physical limits, and so we're really looking to reduce algorithms that, one, consume much more time. For example, collective operations. Optimize those and optimize those in the network. So a bit of a broader a list here of technologies that we have to that instantiate this support. These are several elements that we have in our current product that provide the offload capabilities and give the ability to use those capabilities. That is, it's in the hardware, but the software also uses what's in the hardware. So first thing to notice here is we really are CPU agnostic. The network works over a range for a range of processors, both CPUs and GPUs. And so we're not tied to a particular host architecture. From a feature capability, we have our communication libraries. It's indicated here by the word MPI. But it's more than MPI support. These communication libraries use our offloaded capabilities to accelerate communication, and can be used by any MPI library that wants to use them. So we accelerate both point-to-point and collective operations, which are the dominant ones, obviously, in communication libraries. So this is packaged in OpenMPI. We support a version of OpenMPI. We package a version of OpenMPI that we call HPCX and freely distribute it. Other MPIs also use these libraries. So the libraries are UCX, for those of you that are familiar with them, and HCall. These are the ones. UCX is a point-to-point acceleration library, and HCall is a collective acceleration library. Sharp is a technology that Sharp stands for Scalable, Hierarchical, Aggregation, and Reduction Protocol. This is the protocol that we use to accelerate reduction operations, and I'll talk about it here briefly. Shield is a protocol that lets us recover without software intervention from network failures, from switch failures, from link failures, and this doesn't require any intervention at all from the MPI. It just happens from the application. It just happens underneath the covers as the application is running, if a failure occurs. GPU direct RDMA is used to accelerate communications from and to GPUs. NVMe over fabrics we use to offload the NVMe protocol, the initiator the target and soon the initiator, offloaded from the host, letting the host proceed with other work, and let the network device handle the data that's being sent to or from the NVMe device. We also have technology called multi-host or socket-directed. Has two different instances. What that basically allows is it allows multiple endpoints in a network to use the same card. Those multiple networks can be separate hosts, in which case it's called a multi-host, the multi-host support, or it can be different sockets on the same host, which would be called socket direct. So the Coral systems, for example, use the socket direct capabilities. So overall, what's the impact of these technologies on the particular feature they're trying to accelerate? So Sharp increases the performance of the reduction operations under certain circumstances increases it up to a factor of 10x. And these, for example, these reduction operations are critical both for HPC and machine learning. I have specifics that I'll talk about that here soon. The MPI library, taking advantage of all the features that are available, will speed things up. We've seen even a factor of 35 improvement in application performance under the right conditions. Shield. This is the technology, for the self-healing technology that's in the network. It accelerates recovery from network failures by up to a factor of 5,000. So it reduces the recovery time from order seconds to order milliseconds. And GPU Direct RDMA accelerates both latency and improves bandwidth by a factor of 10 for communication involving GPUs, GPU to CPU, GPU to GPU, either of them. When do I have to end?
35 after.
Okay, 35 you said?
Yeah.
Okay. So Sharp. As I said, Sharp stands for Scalable Hierarchical Aggregation and Reduction Protocol. This is a protocol that was developed as part of the Coral program. The basic concept behind Sharp is it will do aggregation and reduction operations in the network. And so what does that mean? So aggregation and reduction operations include barrier, reduction operations, both reduce and AllReduce. There's a reliable broadcast, and there's an ability to use these for several other collective operations also defined. So basically what it does is it takes so it takes multiple data from multiple sources and reduces it and produces a single result. Now the way it does it is within the network. It builds a logical reduction tree. So the blue stars here indicate the sources of data, which are the hosts. The red stars are the reduction nodes, which are the switches. And each process will inject data into the network and to initiate the reduction operation. And when the reduction operation is complete in the tree, so the reduction will happen up the tree, going up the tree step by step, and then the root will distribute the results to everyone, to the processes that are participating in the operation. If it's not a rooted operation like reduction, and that's the only involvement that the host has. So on the host side all you have to do is inject the data and wait for the answer. You can go off. Everything happens asynchronously. A few things about the support. One, because the switch has a high radix, these trees can be very shallow, and the volume of data that goes through the network is reduced at every step by the radix of that particular reduction node. So in principle, a reduction node can be up to like a factor of 64. So for very, very large systems, you can have trees that are of depth 3, or I don't think there's any system in the world. Well, there might be. You may want to go up to depth 4 on really, really large systems, like order 100,000 or so. But very, very, very shallow networks. The big the other thing, as I noted, the data goes into the network once, as opposed to host-based approaches where the data, if it's a reduction operation, the data will go into the network, typically log n times. And so there's a lot less data flying around the network. So for small reductions, that in itself may not be, the bandwidth is not the issue, but the fact that you're going into the network once is the issue, and you're going through a very short data path. So you get, for short messages, you get large improvements in performance with that. For large data where network bandwidth is the issue, you benefit from the reduction of factors of, on the order of 20 at every step in the tree. And so a big reduction in network bandwidth, and also if you have if your network topology is such that it's it's a blocking topology, that doesn't affect Sharp. Sharp just goes on individual links. So the fact that you don't have globally, maybe you have less links doesn't impact Sharp at all. Sharp has the paths that it needs always has the paths that it needs. So it's very high performance with that respect. So the expectation here for the large data is we'll be getting roughly 90% network bandwidth in terms of throughput for reduction operations. So much more efficient than you can in a CPU-based approach where you have to somehow try and pipeline what's happening on the host and what's happening in the network. So it really takes advantage of the very large radices that you have in the network. From a feature perspective, Sharp supports all the reduction operations defined by the MPI and SHMEM standard, and other like UPC and the like too. Except the only operation that's defined in MPI, it's not defined in other specs as far as I remember, is the product operation. So we don't do products there. We support the operand types are signed and unsigned integer and floating point data. Size of the operands are 60 and 32 and 64 bits. The vectors, there are two protocols. There's one that's optimized for latency, and a second protocol that's optimized for bandwidth. In terms of performance, so the I have latency measurements from the OSU AllReduce benchmark here. These are for small. These are use the small data protocol. 8 blue on your left hand side. The blue line corresponds to reductions of 8 of an 8-byte 8-byte operands, 8-byte total size of from 2 up to 128 nodes. Brown is 128 bytes. Solid line is Sharp. The dotted line is an optimized host-based approach algorithm. So this also uses hardware acceleration. If you take a comparable algorithm in other MPIs, it's typically twice. Latency is typically twice that we see here. So the point here is we're trying to do is a comparison between what Sharp does and a very well-tuned MPI reduction operation. A few things to note about here. So first of all, it's clear. I mean, this is what it was designed to do. That the latency of the AllReduce operation using Sharp is better than that of using the host-based approach. 128 bytes is about a factor of 2.1 difference in latency. The other thing to notice is the Sharp latency is very flat. You see this knee here in the latency. Most of the latency comes from going through these aggregation nodes, those red stars that I showed in the figure before. And this knee here simply reflects going from a one-level fat tree to a two-level fat tree. So you're going through one aggregation node to two aggregation nodes. The size, the radix of the operation, especially for small data, has very little impact on the latency. So, yes.
These are switch nodes, right?
These are switches.
Yeah.
Not nodes. It's actually in the switch ASIC. Yes, that's right. Similar type of data for larger reductions. So this reduction, these are for 1K, represents, the blue line represents a 1K reduction, the brown represents a 2K reduction. This actually has to use pipelining to the protocol because of the vector length that the short protocol supports. So pipelining actually at this size gives even better performance, better relative and absolute performance improvements than the 8-byte reduction does. So the factor of improvement for 128 bytes, and if I remember it correctly, it was a 2K, is about almost a factor of 4. So this really does accelerate those operations. Larger systems. This is data from a 1500 node Dragonfly Plus topology. Again, the message here, we see that sharp. This time the latency is presented as a function of data size at a fixed size of 1500 nodes, and we see about a factor of 5 at 2K, about a 2K message size, about a factor of 5 improvement of performance in sharp relative to the host-based approach. This is for 1 process per node, for n processes per node, where n is for 40 processes per node, where there are 40 cores on the system. We see the improvement is even greater. It looks like it's about a factor of 6 to 7 improvement in latency. So as the size of the system grows, so we're at a 3-level fat tree here. The benefits of sharp are certainly starting to show even more. In terms of applications, so here's some data from a small benchmark code called Mini AMR, which uses which is a mesh refinement code. Uses AMR code. We see 28 nodes, 8 processes, 8 nodes, 28 processes per node. We see there was about an 18% improvement in the code performance when using this operation. So this is data from Ohio State, from DK Panda's group. As I mentioned, one of the other capabilities that we enhance is GPU to GPU support. We have using our card rather than we're able to improve latency between GPUs by about a factor of 10 relative to one does not use GPU direct async. And bandwidths are also improved by about a factor of 10. And so what's done here is we're basically able to bypass using the CPU for all but some control aspects of the protocol. And that's how so we don't have to copy data to the CPU and then have the CPU somehow send it to some others. And that's how we improve. That's one of the ways that we improve performance there. So that's a very, very brief description of 1.5 features that we have in our hardware today. There are other very interesting features, but because of lack of time, I won't get into them. But I'll go and talk a bit about our next generation technology, which is our HDR technology, our 200 gigabit per second technology. This is technology that is due to hit the market this year, and so people in the room will probably be experimenting with it later in the year if you do anything if you do any sort of computing. So just to hit the highlights of the HDR technology. One, as I said before, the base speed is 200 gigabit per second. It's backward compatible, so that the HCA that comes with this is called ConnectX-6. So ConnectX-5 is the current DDR HCA. ConnectX-6 is the HDR HCA. It's backward compatible with all previous generations of InfiniBand. The switch, the InfiniBand switch, the HDR InfiniBand switch is called Quantum. It's also a 200 gigabit per second device with 40 ports. So we've gone from 36 to 40 ports, 36 EDR to 40 ports at HDR. But there's an additional feature here is every port on a port by port basis can be split into two HDR 100 ports. And so you can build topologies. If HDR is the speed that you need, you can build.
Is that going to be using a 50 gigabit per second per lane?
Yes.
Splitting 4 lanes to 2?
Yes, exactly, yeah. And so as long as you use the HDR 100 cards, you can go up to 40 ports, up to 80 ports running 100 gigabit per second. So you can build larger networks with those speeds, or you can use it, Spectrum 2, that's due out later this year, is the corresponding Ethernet switch. So we'll also have some ports running at 400 gigabit per second, in addition to running at 200 and 25 and 50 gigabit per second. It also is backward compatible with previous generations of technology. The Bluefield device that we have is a system on a chip. In a single die, it includes a host channel adapter, and the current device includes 16 ARM cores. It has a few different instantiations. One is a card, and the other is more of a box. And the with the ARM, then the ARM cores on that SoC are user programmable with user level tools that you're familiar with, the GCC set of tools. And so that device lets users have control over offloading processing of network data. We also have a corresponding set of cables, both optical and copper, to go with the solution, and we continue to improve support or add support to our communication library, or our HPCX product, to support the HDR, the new HDR capabilities. So HDR switch really is the most scalable switch in the market. It goes up to 80 ports per switch. It can go up to 3,200 nodes with only with 2 levels in a fat tree, and can go up to 128,000 nodes if you go to 3 levels in the fat tree. So you can build very large and shallow networks with this, much larger than you can with our competition. What competition provides. So you can see here there's savings both in terms of cabling cost, because you have less switches, less infrastructure, especially if you use the HDR 100 capabilities and use the 200 in the backbone. You can have a large savings in terms of costs. So a comparison here between a few different systems. If you build the systems with HDR using the HDR 100 or the 100 gigabit signaling capabilities that provides, comparing it with Intel OmniPath. So if you take a system of size 384 nodes, which is you can or 400 nodes of HDR 100, you can build with 15 switches. and 400 cables, 2-level fat tree. With Intel OmniPath, a similar size, just slightly smaller. It takes more switches, 24 switches, and many more cables, almost twice the number of cables. So really, in terms of part count, in terms of part count, there's and system size. You know, the system sizes are similar. Part count is much smaller, using is basically half, and therefore the cost is also greatly reduced. Is reduced using the HDR 100. Similar with the chassis nodes. As I said, we can build very large chassis switches with the 80 ports of HDR 100. So with 1500 node system using HDR 100, it requires one chassis switch and 768 cables using quantum. Same size system with Intel OmniPath. You use 2 of their chassis switches, about 3 times the number of cables, and about twice the amount of power. Almost 3 times, about 2.5 times the amount of power to power these systems. Another thing that's coming in with the HDR is there's been an effort to make the network much more visible, to be able to get more information about what's going on in the network at a given time. So there are mirroring capabilities that can be triggered by events such as congestion or buffer usage or high latency, or that is operations that happen within conditions that happen within the network that are detrimental to performance. Can trigger some sort of reporting. You know, in this case, mirroring is used for reporting to get information about the current state of the system. So one can get much better feeling for what's going on in the network than one can today. There are also histograms for measuring QDEPs, so you can look historically and see what system utilization looks like. Yeah, I think that covers. So overall, we really do provide, InfiniBand really does provide the best return on investment here, with lower cost, both CapEx and OpEx, and increased application performance. So in weather, we've demonstrated improvements of a factor of 1.9 in application performance. In automotive, a factor of 2. In chemistry, a factor of 1.4. Genomics, 1.3. And molecular dynamics, a factor of about 2.5. Improvement in application performance. So using all the capabilities that we have built into the system. So that's it. Or if there are any questions, I'd be glad to answer them.